Today I'm going to talk about exponential growth bias. So the first thing that I need to explain is what is exponential growth. Okay, I will try to keep the explanation as simple as possible so that even if you don't know much about mathematics, you can still understand. I will be, working with an example that does not require mathematical equations, but for the benefit of those who understand equations, I will just show or describe what an exponential function is. If you visit the Wikipedia, you will see the definition that's given to the exponential, that's given for the exponential growth function. And exponential growth function can be written in the form y is equal to ab power x, where a is greater than 0 and b is greater than 1. So if a is positive and if b is greater than 1, then y is equal to ab power x is an example of a growth function, okay, that is exponential. The second thing that we have to pay attention to is the bias aspect of this function. So this is interesting from a very particular angle. The word bias suggests that it is something that maybe can be addressed, can be removed. So let's see whether that's really possible, or whether it's something so deep and ingrained in our makeup, in our perceptual abilities, our cognitive abilities, that it's really hard to escape the exponential growth bias. So what in fact is exponential growth bias? You see the function that we have here, y is equal to ab power x. As x increases, value for y will also increase. So when you ask people to estimate the value of y for different values of x, you'll find that as x get very large, or not even very large, but reasonably big, you'll find that the estimations for y start getting really off the mark. People are really bad at making estimates for y. In fact, people consistently underestimate how fast the value of y increases. Okay, it's not that they get it. The estimate is obviously wrong. I mean, it's easy for people to know that y will increase, but they underestimate how fast the value increases. And this bias has many profound consequences. For example, we are living in the middle of a pandemic, the coronavirus pandemic. And you can see that initially, most people found it difficult to acknowledge how fast this virus could spread. Okay, so that would be an example showing how the exponential growth bias can have an impact on the behavior of people. You have many examples of exponential growth functions in various fields, from biology, physics, finance, computer science and internet phenomena. So we talked about exponential growth example in biology by referring to the coronavirus case. In physics, if you look at nuclear chain reactions, okay, where you have one particle hitting a target particle, that target particle splits into two others, sub particles, and these two go and hit, other target particles, and you have, and each, if at each and every step energy is released, what happens is, in a very short period of time, you have a massive release of energy, and you have an explosion. Okay, so that's a clear example in physics. You have many other examples, like even audio feedback. That's something that we have experienced, where you have like a feedback loop. Okay, so you have a signal coming in, gets amplified, and then what comes out gets back in and amplified again. So the value, the amplitude of the signals just increase very quickly and very rapidly and overwhelm the audio devices. There are so many examples. In the finance world, on the positive end, you could look at compound interest as an example, and Ponzi schemes and pyramid schemes can also be viewed as exponential growth functions as well. Of course, all these functions don't grow forever. They always hit the limits of the system, and then they collapse. But let's for the time being not go into the boundary conditions that would stop something from continuing to grow forever, and never stopping to grow. Okay, that's beside the point. My concern here is to try to focus on the bias aspect and try to explain that. Well, just to complete the picture of where these functions appear in computer science, most people have heard of the processing of the processing power of computers increasing rapidly over time, and there's so many. Even simple things like the resolution of screens. If you look at the last example, example area, the internet phenomena category, internet memes, viral videos, all these grow following the exponential growth curve for obvious reason. Okay, so if you get a video that you like, and if you send it to two more people, and these two people like it and send to two of their friends, it will get spread very quickly. All right, so that's for the examples of growth functions in our daily life. So after describing what exponential growth functions are, let me now create a very small scenario, a very small scene where that would be suitable for a little problem. Okay, let's start with this. So let us say we have a little house, okay, and there's only one room in this house. So let's wait for this house to get constructed here. I will describe a problem to solve in this house, and then we'll start thinking about we'll see how this is related to the exponential growth problem. Okay, so let us say that this is like a simple house. All right, let me just sign up. So this is our little house, and what I want to do, you can see that it is a very small room in a house. It's only one room. It's a strange house. There's only one room, but it is a very small space. When I sign into this little application here that constructed the house, I won't go into the details of the application. There will be details about that in the description below if you're interested in creating props for your classroom in order to explain things more clearly, more easily. These links might be of interest to you. So we are in this very small room, and you can see that it's got like 4x4. It's got like a 4x4 grid. Okay, so 1, 2, 3, 4. 1, 2, 3, 4. All right. And what we want to do is simply this. We want to create a little block and place it inside this room. Let me do that. So let us say I'm going, just so that it stands out, okay, I'm going to pick, let us say, something that stands out, like the black block that I'm going to place here. Okay, so what we need to do is simply this. We want to place one block in the one of the grid, and in the second square I want to double that amount. Okay, I want to place 2. In the third square, I'm not going to place 3, I'm going to place actually 4, because it has to be twice the amount that was in the previous square. So it's going to be 1, 2, 3, and 4. Okay, and now we have a problem. We have already started to touch the ceiling. Okay, so what I'll do, I'll remove the house. Okay, and consider the problem very simply. The only reason for me to introduce this small room here is that you get a sense of the space inside that room. So that in your mind you have an idea, okay, this is how tall my body is, and I'm going to place this block. I should have said these blocks, I should have said that all these blocks are 1 meter cube. Okay, and all right, so you have an idea of how much space you would need, if you want to keep on doubling the number of blocks and keep adding to the next square. So let me clear this scene, and we will try to solve this problem. What is the problem again? The problem is this. We have a grid which is 4x4, and we want to place 1 block on the first square of the grid, and then double that amount and place on the second square of the grid. So it will be 1 times 2, 2 blocks for the second one, and 4 blocks for the third one, etc. We keep on going, and then we'll try to find out, after going through all these steps of doubling the blocks every time we are going to place them on the next pre-square, if we add all the cubes that fits this 4x4 grid, how many of these cubes there will be. We need to estimate that. So that's the problem. If you didn't get what I'm saying, we'll have a chance to revisit again. So let me clear this. Let's see. Let me load this slide. Okay. So we are going to pay attention to what's happening here. Okay. So now let's forget about the house and the floor and the blocks in it. We are going to simplify further the situation so that you only have a simple grid like here. Okay. And the task is to place one block on one square. The grid, the area that we are allowed to place our blocks are 4 by 4. Let's focus on this. So I'm going to load next frame, and here it is. So now we don't have the house, we only have the blocks. And what I have done, I've placed one block here on the first square, I've placed 2 blocks on the second square, I've placed 4 blocks on the third square, and I've placed 8 blocks on the fourth square. All right, so you might recall, at least for people who, for viewers who might be familiar with a very old story about a chessboard, and you had to place 1 grain of rice on the first square, 2 grains of rice on the second one, double that amount, 4 grains of rice on the third one, till the end, till the 64th square, and you'll find that the number of ice grains would be so huge that it's quite incomprehensible, literally. But let's forget that example. I tried to simplify things further here so that you can see it and what's happening, and then we can derive some insights. All right, so in this case, we have this. So the next step would be to double the amount here that you have here, which is 8. So you want to put 16 here, right? Let's see. Can we put 16 here? And after putting 16, we'll have to put double 16. That is 32 on this one. As you can see, the height of these blocks will grow very fast. So we'll use a trick to try to keep things manageable, okay? Because I don't want, I have the other thing I should mention is that if I don't do this, I will run out of memory. There are some constraints that I have that prevents me to keep on adding as many blocks as possible. So let me load the next let's call it frame, and you'll see what trick I used. Okay, so I thought that if we need 16 square, a stack of 16 squares to be placed here, why not, use a different cube to represent a stack of 16 cubes? Okay, so that's what I have done here. That's like a legend. It says 1 black cube represent 16 cubes. So what I'm going to do is I'm going to load the next one to demonstrate that here we have 16, and here, because we had to double this amount here, so I'm using 2 black square, and here I'm going to use 4 black square. And remember, each square represents 16 white. Each black cube represents 16 white cubes. All right, so that's very easy to understand. Okay, so when you have here, you have like a stack of 16 black cubes, but if you were to use the white cubes, it would have been 16 times 16. Okay, and this column here would have been very, very high indeed. And we know 16 times 16 is 256. So we want, by using this little trick here, we have been able to use less cubes. It's kind of, we are using an abstraction. We have created an abstraction to represent something, and then we are trying to cram everything in a very limited space. Okay. So we were at the fourth frame. I'm just trying to remember so that I don't. We go to the fifth one. Okay. Well, for the fifth one, we apply the same principle. Okay. So I find a new colored cube and use that to represent a stack of 16 black cubes. Okay. And then I place it here. And I'll go through and say, okay, I'm going to double this number and place it here. And we can continue. So we were on the fifth. Now we go on the sixth. Slide. Now we complete that. Seventh slide. Remember, we had a square of 4 by 4 meters. So we have 1, 2, 3, 4, 1, 2, 3, 4. Okay? And now I'm going to place the pale brown cube the same way. To fulfill everything. Have we reached slide 7 or so that's 8 then. Let's do this. Okay. So you have slide 8 that actually, just had all these objects in the right place. Let's only focus on these objects here. The others are, for me, like basically notes. So each pale brown cube represents 16 of the darker brown cubes. Each darker brown cube represents 16 of the black one. Each black one, 16 of the white one. Okay. By using this abstraction, I've been able to squeeze the visualization into this space. At least it fits on the 4x4. Okay. But abstractions have their limitations. Okay. Cognitively, it's not. I lose information whenever I abstract, whenever I summarize, in order to fit a representation within a constraint. I'm actually losing information. Okay. Yes, the representation might be correct, but the power of representation gets lost by the meaning gets eroded a little bit. But you can see that when you look at this representation, it doesn't give me any idea. It gives me like a rough idea of how many cubes would actually fit this 4x4 grid, the floor of the house, as it were. And, if there were no roofs, this is the number of cubes that would fit this small place. But this representation is not powerful enough. Okay, but that's the best we could come up with. And so if we were to add all these cubes together, so here you have 8 plus 4, 12, 13, 14, 15. Okay, so you have 15 here. And you have, for each and every section, you have 15 cubes, and each of these cubes have a particular value. So it would be 15 times 1, 15 times 16, added to 15 times 256, added to 15 times 4096. Okay. Why is that? Of course, because we know that every light brown cube here represents 40,096 white cubes. So you can immediately see that this number is quite big. All right. And if you add all these together and express it as white cubes, you get 65,535. Okay. If you were to express this mathematically, you would be using this notation. It's basically, for I is equal to 0, so if you have like 4 by 4, what do you have? 4 by 4, it's like 16 squares, but you're starting with 0, so the last square will end at 15, right? So n is equal to 15. N is 15 here, so it's the sum of 2 to the power of I, for I ranging from 0 to 15, because of 16 squares. We start with 0, we end with 15. This formula gives you the total number of cubes that you would have. So it would be 2 to the power of 16 minus 1. So 2 to the power of 16 is 65536. If you subtract 1, you get 65535. If you want the proof to this equation, well, you can prove it by induction. But again, I really wanted to present things here very simply so that you don't get lost in the mathematics. We are still trying to figure out, the bias, the exponential growth bias, and get a feeling for it. Okay, so the most important thing that we needed is that first an understanding of the problem. So we have a very small space. We want to place one block on one square, double that number of blocks on the second one, keep doing going on until all the 16 blocks are covered, add all these blocks together, and look at that number. Okay? And we also said in the beginning that each block was 1 meter cube, so it's 1 meter high. So if we were to stack all these blocks, one on top of the other, okay, how high would that column be? That would be 65,535 meters high. Okay, so this is a quite high value. All right. And if you look at, how high this value is and try to compare it to natural features in the real world, you'll find that, the tallest building in the world, let me sign out of this application so that we get rid of these hamburgers. Okay, so now you see that the Burj Khalifa is 828 meters. Okay, so that's how that building is. So in your mind, when you visualize it, it's the tallest building. In fact, often at the in the higher levels, the higher level rooms are above the clouds, can be above the clouds, sometimes. And how many? Now the question is, how many of these buildings would you need so that the height, the total height, will match, the 65,535 meters? And you'll find that you need 79 times of the Burj Khalifa stacked on top of each other. So this sounds quite incredible because you have this little space, 4x4, and you only asked to put a cube on the first one, double it, and put the double, the 2 on the second one, 4 on the third, 8 on the fourth, and add all these cubes together. And most people, if you ask them, how high is that stack, it will be very difficult for them to estimate it. Okay, they will have to do some mental calculation and then maybe give you an answer. So all this that I described here that took quite a while would be done very quickly by those who can actually make a good estimate, but it won't be like a gut feeling of how high it would be. So that's the bias, okay? That's the exponential growth bias that we've been talking about. Just for fun, I mean, this stack is so high that you would need 7 times the height of Mount Everest for these heights to match. Okay, and now if I ask the question, what if instead of having to place these cubes on a 4x4 grid, okay, if instead of having to place it on a 4x4 grid, you had to place the cubes on a 5x5 grid, how high would the stack of cubes be? Okay, if I just ask that question, if you are watching the video carefully, you would actually already know the answer. But surprisingly, the height of this stack would be so, the magnitude would be so high, so large, that you would need to go into the astronomical realm. So we have to talk about the size of the planet Earth. Okay, so what we will find is, if we try to place 1 meter cubes following the doubling rule that I mentioned on a 5 meter by 5 meter grid, okay, and you add them up and you place them one on top of the other, the height would be 33,554,431 meters. Okay, and what is the Earth's radius? It's only 6,378,100 meters. But in this case, even if we increase the dimension of the problem just by a little bit, the results is mind-blowingly big. When we ask people to make an estimation, the estimation is always an underestimate of what the actual value would be. So, just to summarize, what we've done in this clip is to explain exponential growth bias, and we spent more time talking about a simple problem and demonstrated where the bias was, and once we've done that, there are some issues that comes up. Okay, one of them is, how can we improve the visualization? Can it be done? Can we actually improve a visualization that will allow us to lose this bias? I feel it's not possible, because every visualization comes with a certain constraint. And in this case, our constraints was the the computing constraints. I could not, in this environment, use that big number of cubes without overwhelming the system. The platform I am using would not allow me to do this. The second thing, on a more simpler level, I had to resort to abstractions. That is, I had to create a kind of second order representation. What is an abstraction? It's kind of a summarizing concept. So I would invent like a black cube that would mean something else. Okay, so the black cube means 16 of the white cubes, and I do the same thing at each and every step. I'm not sure whether the mind can actually hold all these different summaries, all these different abstractions together and still makes sense. In fact, it actually becomes counterintuitive, because here it gives the wrong impression. If we didn't know the meaning of these black cubes, it kind of distorts the view a little bit. It's not very useful. And the same issue arises when you try to look at the vertical axis of graphs trying to represent exponential growth functions. They try to compress the graph at higher values of y. So you have a logarithmic scale, as it were. So when it seems that we have to introduce distortions in our visualization space in order to accommodate the data representation, and these distortions obviously distort the meaning, and our brains cannot quite manage that. Okay, so I think that's completes the little presentation I had about exponential growth bias. Okay, so if you liked this clip, just hit the like button or subscribe, and you know what you have to do to help the YouTube algorithms a little bit. Okay? Thanks for your attention.